Now, the next section we have today is why is it that when you have a molecular compound, you actually have to tell how many atoms there are in it. So for example, carbon dioxide, we exactly say how many atoms of carbon and oxygen we have. Dinitrogen monoxide, we have to say how many atoms of each we have. Here, how many atoms we have, and here as well. The reason for that is that in a molecular compound, we don't have something similar to ionic compounds, which is a metal that gives electrons, and then non-metals that attracts electrons. When we have a molecular compound, we have what we call electrons are being shared. And the big question is how many electrons are being shared at one moment? That is something to look into. So for an example, we can have, so let's see, if I have water, so water like this with one hydrogen like this. Let's put oxygen. I'll give you a few examples to explain what it is. So we have like this. Perfect. If you have water like this, what's interesting is that we know that using the Lewis dot diagram, that we have the hydrogen with one electron on the outer shell. Same thing with this one. And around the oxygen, we have 6 valence electrons. So here we have 1, 2, 3, 4, 5, and 6. If we are showing here an example of molecule of water, we know that this is what it looks like. And this is like a picture in time. What's interesting with science is that we know that electrons are moving very fast, almost to the speed of light. So what happens is that if you take a picture, you can know where they are, but you have no idea on the speed they have. On the other hand, you can measure the speed of electrons, but you don't know where they are at any given moment, given the speed they have. So here what we have electrons that are moving. Oops, I will pick it up later. We have here, oops, another one. We have here oxygen that wants to have electrons to cover its outer shell. So what happens is that every so often, this electrons here tends to be going closer to the oxygen. So what happens here is that this section here would have one more electron, so this end is more negative. And for a moment, this hydrogen is now positive because there's no electrons right around it. So here you end up with hydrogen plus and OH minus momentarily. And that's why water is so amazing. As soon as this is like this, what happens is that this positive hydrogen says, okay, I'm positive, I want an electron again. So what happens like this? So we have, let's get the blue again. So we have the blue here. We have this hydrogen calling for electrons, but the oxygen still wants to have their electrons. So what happens is that this hydrogen gets closer to the oxygen, and therefore you end up here with the hydrogen and oxygen, and this part is more negative, and now we have a positive hydrogen. So here what happens is that you end up with this part negative or this part, and it's going back and forth. When you go into grade 10, you will see that naturally there's a portion, there's a number of water molecule that will go straight to this. But as soon as they're like this, they will go back to water here. And that will help us with pH next year. How is that possible? We have electrons that are moving all the time. Very good. So let's see if I can take another example that could be fun before we get to the nitrate here. So we have a situation where we have, for example, carbon dioxide, carbon here with 4 valence electrons. Then we have here, let's get the oxygen. I like oxygen in red, it shows nicely. So we have the oxygen. Very nice. So this is the Lewis diagram of a carbon dioxide molecule. Now this is a snapshot that shows us where the electrons are at one moment when everything is good. However, we know that the carbon here does like to have electrons, but oxygen too. So if it happens that you have electrons that are attracted by the carbon here, more electrons are going this way. So this tends to be a little bit more negative. And for a moment, this is a little bit more positive at the end of this molecule. But as soon as this is positive, electrons from this side will go on this side here. And if that's the case, you end up with a moment where more electrons are here, and this end is a bit more positive. And if the oxygen are getting more electrons, what happens is that you end up with negative, and the middle part that is more positive. So what happens is that you have a change on the affinity or the electron affinity depending on where the electrons are. If it happens for a moment that the electrons are on this side, and here we have carbon that is now positive, what will happen is that we get something that is interesting. So here is an example on how other molecules are stable. The carbon, if we have electrons that are moving to the oxygen, we have more positive. The carbon momentarily will say, well, if there's some electrons around, I would love to pick it up. And if there's oxygen, like this, what will happen is that there's an oxygen that has a valence of valence electron, 6 valence electrons, there you go, and then will join to these two so that now it has 8. This has 8, this has 8, and this has 8. But what is interesting is that carbon here has 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So somehow this big group of atoms have a charge. And if I am to take all of these, you end up with 1 carbon, you end up with 3 oxygen, but somehow there are 2 electrons that have been added to make sure that this is stable. And this is what we call it's a polyatomic ion. There's 1, 2, 3, 4, so 4 atoms, and it is called carbonate. We have here an ion that contains many atoms, -2. If it happens that we have calcium close by, it will become calcium carbonate. If it happens that we have a magnesium that is 2+, then we have magnesium carbonate. And these exist because if you think of shells, for example, of the different animals in the ocean, the shellfish, for example, they all are made of magnesium magnesium carbonate and calcium carbonate. Where's the carbon dioxide coming from? It is coming from the water, and it is part of the metabolism where somehow there's a movement of electrons to create new substance. Here again, electrons are always in movement, creating new matter all the time. So let's see if I can look at another example with you. So here's an example on how we have here dinitrogen monoxide, and how, because the electrons are moving all the time, it allows us to have a configuration different in a 3-dimensional world, but still with the same chemical composition. And that's why it's hard sometimes to say, are some of the atoms in a molecular compound, so they're sharing 1, 2, 3, or more electrons? It's all part of how the atoms are interacting and where electrons can be. So let's see if we can look at the first one here. We have a nitrogen here with 5 valence electrons, nitrogen with 5 valence electrons, and oxygen with 6 valence electrons. That works well. This nitrogen shares 3. This nitrogen shares 3. That means that we have 8 valence electrons. It's happily the octet. This idea of having 8 electrons on the outer shell works. Here we have nitrogen that shares 2 here with the oxygen. What happens? So the nitrogen gives 2, but the oxygen here is not sharing any. So we have here 8 valence electrons, and here we also have 8 valence electrons. Here everything is wonderful. But because here we have an oxygen, and the oxygen is getting 2 electrons from the nitrogen, this end of the molecule has a little negative sign. And that's why we end up with this one here. But electrons are moving at the speed of light. So what happens is that because we have a little more positive charge here, electrons will start moving, and they're moving at the speed of light. So what happens? Electrons are starting to move. So here we had 3 pairs of shared electrons only. So here there was only 2. And here you end up with, again, dinitrogen monoxide, but here you have 2 pairs of shared electrons. How is that possible? So here what we have nitrogen with 5 valence electrons, we have nitrogen with 5 shared electrons, and here we have our 6 electrons. But what happened though is that here this nitrogen is sharing 3 and this one only 1. That gives us 8. Here we have at this time the nitrogen that is sharing with the oxygen 2 of these electrons. So here we have 8 electrons, and here for the oxygen we have 8 electrons as well. Because here we have more, so we have 5 valence electrons and we have more electrons from the sharing, we have this part a bit more negative. So earlier this side was negative, now it's going on this side. In the middle here we had our 5 here, and it's sharing electrons on this side and sharing on this side. So this one here has an affinity that tends to be more positive. So the consequence here is that we have electrons that are keeping this and this well together, but the way the electrons are in the molecule can change. And that's why if you are looking at this, the way the compound is from here to here will go back and forth, will change because the number of electrons are being accounted for, but the electrons are moving. And because they're moving at the speed of light, it can change how it may look if you were to take snapshots of these molecules, but they're still like this. And that's why when we have molecular compounds, we want to make sure we outline how many of each of the atoms we have. And then we need to look at the work to try to figure out how can we have a structure that makes them stable. And this is the last topic for the live today. And if you have any other questions, put them in the comments below. I will be more than happy to either answer them or create new videos on this. Otherwise, I'm going to put here a link to another video on chemistry. You'll see we'll have so much more to learn.